you about the trapezoidal rule. Now, how do ants get rid of body odor? They use deodorant.
First thing we're going to talk about is the definite integral as the area of a region. If f is continuous and non-negative on the closed interval from a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is equal to the integral from a to b of f of x dx. So this theorem is just proving to you exactly what we were just saying. The integral from a to b of f of x dx is just giving you the exact area under the curve of your given function f on the interval from x is equal to a to x is equal to b. It's adding together the areas of an infinite amount of rectangles in that given region in order to give you the exact area under the curve on that closed interval. Now, the trapezoidal rule says let f be continuous on the closed interval ab. The trapezoidal rule for approximating the integral from a to b of f of x dx is h over 2 times the quantity f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 all the way to plus 2 times f of x sub n minus 1 plus f of x sub n. Moreover, as n approaches infinity, the trapezoidal approximation approaches the integral from a to b of f of x dx. So, to approximate the area under the curve, you are creating trapezoids rather than rectangles. Remember Riemann sums, we were creating rectangles using left, right, and midpoint approximations. Now we have the trapezoidal rule where you create trapezoids under the curve and you can approximate the area under the curve and approximate the integral from a to b of f of x dx. And this says as n approaches infinity. So as the number of trapezoids that you make approaches infinity, you are getting closer and closer to the integral from a to b of f of x dx, the exact area under the curve. Now, how did we get the trapezoidal rule? Where did this come from? Well, let's explain this a little bit more. Imagine that we have a function f graphed on this coordinate plane right here, and we want to find the area under this curve over the given interval from a to b, this closed interval. What we would normally do is break this up into subintervals. Here we have 4 subintervals, and we would create rectangles under the curve and add up each of the areas of those rectangles and get an approximate area under the curve. You could use a left-hand approximation like this, you could use a right-hand approximation, or you could use a midpoint approximation, but you either get a large overestimate or a large underestimate. What you want to do instead is create trapezoids. Trapezoids fill more of the empty space here that you would normally lose with Riemann sums. So if I create a trapezoid, it actually gives you a more accurate representation of the area under the curve. So now we just need to find the area of each trapezoid and add them together. The area of a trapezoid formula, remember, is 1/2 the sum of the bases times the height. What's tricky about this is that the height of a trapezoid is the perpendicular distance between the two bases. The bases are 2 parallel sides. Now, in this first trapezoid right here, you can see that the 2 parallel sides are actually here and here. The height is actually going to be on the x-axis right here. So you have to imagine that each trapezoid is actually on its side, where the height is on the x-axis and the bases actually go up like this. If we want to picture the bases again, these are the bases usually in a trapezoid, and if you were to rotate it on its side like we have over here, the bases are actually going to be the vertical distance between the x-axis and the function. If we want to derive this trapezoidal rule formula, here's how it looks. We have delta x, which is the height of each trapezoid. And remember, delta x we find using the formula b minus a over n. That gives us the height of each trapezoid. That also gives us the base of each rectangle when we're using Riemann sums. Next, to find the length of each base, remember the bases are the vertical sides, you would plug your x value from each interval into the function. So each x value you're going to plug into the function. So this would be f of a. If this was x sub 1, this would be f of x sub 1. If this is x sub 2, this height right here would be f of x sub 2. Same thing here, f of x sub 3 would be this height right here, and then this height right here would be f of b. Now let's go ahead and find the approximate area under the curve using the trapezoidal rule. To do that, all we have to do is find the area of each trapezoid and add them together. So the area of this blue trapezoid is 1/2 the sum of the bases, f of a plus f of x sub 1 times the height, which is delta x or h. Next, for this green trapezoid, 1/2 the sum of the bases, f of x sub 1 plus f of x sub 2 times the height, which is delta x or h. Same thing here, 1/2 the sum of the bases, f of x sub 2 plus f of x sub 3 times the height, h or delta x. And then last but not least, 1/2 the sum of the bases times the height. If we want the total approximate area under the curve using the trapezoidal rule, we just add each of those area formulas together. Now, to get the formula that we talked about in the slide in the beginning, the cool thing that happens is that each term has a 1/2 and an h. So I can factor out a 1/2 and an h. The next cool thing that happens is that each trapezoid actually shares a side. The blue and the green trapezoid share this side. The green and the yellow trapezoid share this side. The yellow and the purple trapezoid share this side. So I can actually combine f of x sub 1 and f of x sub 1, and I get 2 f of x sub 1. Same thing here. F of x sub 2 plus f of x sub 2 is 2 f of x sub 2. And then f of x sub 3 plus f of x sub 3 is 2 f of x sub 3. Now this is where that formula came from that we talked about at the beginning. We have h over 2 times the quantity f of a plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 times f of x sub 3 plus f of b. Each of the endpoints, the height associated with those does not have a 2 because those sides aren't shared with any other trapezoid. But these sides in the interior, those bases are shared between trapezoids. That's why there's a 2 attached to them. Now, if we want to generalize this for any number of partitions, that means any number of subintervals, it would look something like this, where n is the total number of subintervals.
I really hate to bug you, but it's example time.
Now, example 1 says use the trapezoidal rule to approximate the value of the definite integral for the given value of n. Round your answer to 4 decimal places and compare the result with the exact value of the definite integral. So here, we have the integral from 0 to 2 of x squared dx, where n is equal to 4. The interval is from 0 to 2, so 0 is your lower limit of integration, 2 is your upper limit, and we have 4 subintervals. So let's go ahead and determine the height of each trapezoid. The height is the same as delta x, which is equal to b minus a over n. b, our upper limit of integration, a, our lower limit of integration, and n equal to 4. Simplify and you end up getting 1/2 the length of each subinterval, or the height of each trapezoid. Next, we need to plug in the height and x values to the trapezoidal rule. Trapezoidal rule looks like this. So the height is 1/2. That goes in here. Now f of a, f of x sub 1, f of x sub 2, all that stuff is what we have to figure out now. So our first trapezoid has a height of 1/2. This base over here we find by doing f of 0. This base right here we find by calculating f of 1/2, and we have our first trapezoid. Second trapezoid, we have a height of 1/2. This base we calculate by doing f of 1/2. This base we calculate by doing f of 1. Now we have our second trapezoid. Our third trapezoid has a height of 1/2 also. This base we calculate by doing f of 1. This base we calculate by doing f of 3/2. We have our third trapezoid, and last but not least, our fourth trapezoid has a height of 1/2. This base we calculate by doing f of 3/2, and this one we calculate by doing f of 2. So now we have everything we need. So we have 1/2 over 2, h over 2, times the quantity f of 0, which is our first endpoint, plus 2 times f of 1/2, because that's shared by these first two, plus 2 times f of 1, because that's shared by these two, plus 2 times f of 3/2, because that's shared by these two, and then plus f of 2, because that's not shared by anything else. Now we can calculate these by plugging them into our function up here, x squared. So 0 squared is 0, 1/2 squared is 1/4, 1 squared is 1, 3/2 squared is 9/4, and then 2 squared is 4. We can then simplify that further, and we get the approximate area under the curve using the trapezoidal rule here is 2.75. We can then confirm this with a graphing calculator by pressing the math button, scrolling down to press 9. We can then plug in our lower limit and upper limit of integration, our function here, and we're integrating with respect to x. Press enter and we get 2.6 repeating, which shows you that this is an approximate area under the curve. It's not exact, but it's approximate. Example 2, we're doing the same thing. Again, start by finding the height of each trapezoid. The height of the trapezoid is the same thing as delta x, which is b minus a over n. So your upper limit of integration minus your lower limit of integration all over the number of subintervals, 6. So we get 6 minus 0 over 6, which is 6 over 6, which is 1. So the length of each subinterval is equal to 1. That is going to also be the height of each trapezoid. Next, we need to use the trapezoidal rule and plug in our height, which is 1. And then we need to figure out what f of a, f of x sub 1, f of x sub 2 are. So let's go ahead and do that. Our first subinterval, we have a height of our trapezoid of 1. This base we calculate by finding f of 0. This base we calculate by finding f of 1. There's our first trapezoid. Next trapezoid, height of 1. This base we calculate by doing f of 1. This base we calculate by doing f of 2. Now we have our second trapezoid. Our third trapezoid, we have a height of 1. This base we calculate by doing f of 2. This base we calculate by doing f of 3. And we have our third trapezoid. Our fourth trapezoid works the same. Fifth trapezoid works the same. Sixth trapezoid trapezoid works the same. Now we have our 6 trapezoids because we have 6 sub-intervals. We are then going to plug each of these in to our trapezoidal rule. So again, 1 goes in for your height. F of A is going to be F of 0. F of B is going to be F of 6. Therefore, everything else in here, we're going to have to multiply by 2. So it's going to be F of 0 plus 2 times F of 1 plus 2 times F of 2 plus 2 times F of 3 plus 2 times F of 4 plus 2 times F of 5 plus F of 6. Now all we have to do is simplify this. So to do that, we have to plug each of these in to our function, which is the cube root of x. We can plug that all in our calculator, and we end up getting that the approximate area of the curve using the trapezoidal rule here is equal to 7.9081. Now, we can go to our graphing calculator, press the math button, go down to 9, press enter, and then plug in our lower limit, our upper limit, and our function with respect to x, press enter, and we get the exact area under the curve from 0 to 6. And you can see that our approximate area under the curve is pretty darn close. Now, example 3 says concert tickets went on sale at noon, time t equals 0, and were sold out within 9 hours. The number of people waiting in line to purchase tickets at time t is modeled by a twice differentiable function L for 0 is less than or equal to t, which is less than or equal to 9. Values of L of t at various times t are shown in the table. Use the trapezoidal rule and 3 subintervals to estimate the average number of people waiting in line for the first 4 hours that the tickets were on sale. So this is exactly like a problem you would see on the AP test. You have a table and you're using a trapezoidal sum with 3 subintervals to estimate the average number of people waiting in line during the first 4 hours. So we're only concerned with 0, 1, 3, and 4 hours. We first determine the height of each trapezoid. Here's the thing. Anytime it gives you a table, the height of each trapezoid could be different. You can't use h is equal to b minus a over n because you have a table. You don't have a function. So here's what we do. 3 subintervals, right? So we have 3 different trapezoids. The first trapezoid is going to have a height of 1 because our height is on the x-axis. So from 0 to 1, that's going to be our first subinterval. This base over here, we find by doing f of 0, and f of 1 is going to give you the second base for this particular trapezoid. Now don't forget, there's 3 different trapezoids we have to find the area for. We found the area for the first trapezoid. Now we need the area for the second trapezoid. That is going to have a height of, well, we're going from 1 to 3, so that's going to be a height of 2. This is going to be base sub 1. This is going to be base sub 2 for your second trapezoid. Next, our third trapezoid is going to have a height of, we're going from 3 to 4, so it's going to have a height of 1 now. This base we calculate by doing f of 3. This base we calculate by doing f of 4. And then again, we're multiplying by half because that's the formula. Now what we can do is we can simplify this by substituting in f of 0, f of 1, f of 1, f of 3, f of 3, and f of 4. If we plug those in and simplify this in our calculator, we end up getting that the approximate area under the curve from 0 to 4 for this particular function using the trapezoidal approximation is 621. But that's not what it's asking. It's asking for the average number of people waited in line. So this gives you the approximate number of people who waited in line over the first 4 hours. But we want the average number of people. So what you do is you take this number, divide it by 4 because there were 4 hours, and you get approximately 155.25 people. Now this again is the average number of people who waited in line during the first 4 hours. So example 4 says a zoo sponsored a one-day contest to name a new baby elephant. Zoo visitors deposited entries in a special box between noon, t equals 0, and 8 p.m., t equals 8. The number of entries in the box t hours after noon is modeled by a differentiable function, capital E, for 0 is less than or equal to t, which is less than or equal to 8. Values of capital E of t in hundreds of entries at various times t are shown in the table. Use a trapezoidal sum with 4 subintervals given by the table to approximate the value of 1/8, the integral from 0 to 8, capital E of t dt. Using correct units, explain the meaning of 1/8, the integral from 0 to 8 of capital E of t dt in terms of number of entries. So let's go ahead and break this down a little bit. It wants us to use a trapezoidal sum with 4 subintervals. Now, if you look at this table, what we see is that we actually have 4 subintervals. We go from 0 to 2, 2 to 5, 5 to 7, and 7 to 8. That's good. Anytime you have a table, you aren't allowed to use h is equal to b minus a over n because we don't have a uniform height for each of the trapezoids. This one has a height of 2, this one has a height of 3, this one has a height of 2. So it's different for each trapezoid. So since we have 4 subintervals, and this table gives us those 4 subintervals, we're going to have 4 area of a trapezoid formulas. So in this case, we have a height of 2, and the bases are going to be f of 0 and f of 2 for that first trapezoid. For the second trapezoid, we have a height of 3 from 2 to 5, and then your bases are going to be f of 2 and f of 5. For your third trapezoid, we have a height of 2. Our bases are going to be f of 5 and f f of 7. For this last trapezoid, we actually have a height of 1, and f of 7 is going to be your base, and f of 8 is going to be your other base. Now what we can do is we can plug in these given values. So f of 0 is 0, f of 2 is 4, f of 5 is 13, f of 7 is 21, f of 8, 23. We plug those in, we simplify, and we end up getting, using our trapezoidal sum, our approximate area under the curve for this, our approximate integral from 0 to 8 of e of t dt is 85.5. Now what we do is we take this, and it says it wants 1/8 times this. So we're going to divide that by 8. So if we divide that by 8 or multiply it by 1/8, we get approximately 10.6875 hundreds of entries. So it says explain the meaning of 1/8 the integral from 0 to 8 of e of t dt. We're saying that that is the average number of hundreds of entries in the box between noon and 8 p.m.